Precalculus Lesson 25 is Systems of Linear Equations and Applications. We start by solving 3x3 systems of linear equations. 3x3 systems means we have 3 equations and 3 unknowns here. This is section 6.2 in the College Algebra textbook. And let's begin with the system x plus y plus z equals 5, 2x plus 3y minus z equals 2, and 2x plus 3y minus 2z equals 4. I will label these as equations 1, 2, and 3, and make a note to myself that I'm going to start by eliminating z. So just write eliminate z. And what I'll do to eliminate z is, first of all, I'm going to work with, I need 2 different pairs of equations to work with here. And if I look at equation 1 and 2 and add those together, those look good. It looks like z will just disappear from those 2 equations if I add them together. So I have x plus y plus z equals 5 from equation 1, and then 2x plus 3y minus c equals 2, equation 2. Add these together to get 3x plus 4y equals 7. And next, I think I'll choose equation 1 and equation 3. Note that I'll need to multiply equation 1 by 2, multiply each side of the equation here by 2, to result in 2x plus 2y plus 2z equals 10, so that when I add equation 1 to equation 3, the z terms will add to 0. Okay, so adding to equation 3, we get 4x plus 5y equals 14. Okay, and let's give these new equations names too. So 3x plus 4y equals 7, I'll refer to as equation 4. 4x plus 5y equals 14, I'll refer to as equation 5. And to add these 2 equations together, I think I'll try to eliminate x here, which I need to do that, I need to multiply equation 4 by 4, and I need to multiply equation 5 by negative 3. So let's see, 4 times equation 4 would be 12x plus 16y equals 28. Negative 3 times equation 5 would be negative 12x minus 15y equals negative 42. Adding these 2 equations together, we get y equals negative 14. So we've actually solved for y at this point. Once I've solved for y, I'm going to start backtracking and plugging the values as I find them into previous equations. So let's look back at equation 4 right here. And I'm going to look at equation 4. I have 3x plus 4, and I'm going to replace that y with negative 14. So 3x plus 4 times negative 14 equals 7, or 3x minus 56 equals 7. Okay, and from there we get 3x equals 63, or x equals 21. So we've solved for x and y at this point. I'm going to choose one of those first 3 equations, and I might as well grab equation 1 here to solve for z. So in equation 1, we have x, which is 21, plus y, which is negative 14, plus z equals 5. Okay, so 21 minus 14 is 7. 7 plus z equals 5. And then subtracting 7 from each side, I get z equals negative 2. Okay, so we've solved for x, y, and z here. I can write my solution as the ordered triple, 21, negative 14, negative 2. And let's see what this solution means, or how do we classify the system according to this solution. Is the system consistent independent, consistent dependent, or inconsistent? Well, if we have at least one solution, we consider our system consistent, and if we have one single solution, we consider the system to be consistent independent. So that would be the choice here. What does that mean geometrically? Well, geometrically, this one solution, if we imagine three planes intersecting in exactly one point, that's what this one solution would mean geometrically. Now let's solve the system. X plus z equals 0, x plus y plus 2z equals 3, and y plus z equals 2, labeling the three equations 1, 2, and 3. And this time, let's eliminate x, which it looks like it's already missing from equation 3. So I'll make a note, eliminate x. And to eliminate x from equations 1 and 2, well, let's say we have equation 1 is x plus z equals 0. I'll need to multiply equation 2 by -1, it looks like, which would result in negative x minus y minus 2z equals -3. Adding these together, we get negative y minus z equals -3. Okay, we'll call this our equation 4. And now let's try eliminating y using equations 3 and 4. So it looks like I can just add those together. Equation 3 is y plus z equals 2. Equation 4 is negative y minus z equals -3. Adding these together, we get 0 equals -1. Well, that's not good. That's not a true statement, and it cannot be made to be a true statement. So what that tells us, though, is that this system of equations has no solution. Okay, no solution here. Well, what does that mean in terms of classifying the system? If we have no solution, we say that our system of equations is inconsistent. And graphically or geometrically, what would that mean? Well, we could have three planes, each of the three planes intersecting with the other two, just never at all three intersecting at the same time. We could also have one plane that intersects with each of the other two planes, but the other two planes never intersect with each other. Or we could have none of the three planes intersecting at all, and we could think of those as being three parallel planes. Now let's solve the system. X plus y plus z equals 1, negative x plus 2y plus z equals 2, and 2x minus y equals -1. Again, labeling these equations 1, 2, and 3. And making a note here that equation 3 is already missing z, so that's a good variable to choose to eliminate here. So let's eliminate z. From equations 1 and 2, I can multiply equation 1 by -1, which would be negative x minus y minus z equals -1. I would add that to equation 2, negative x plus 2y plus z equals 2. We get negative 2x plus y equals 1. Okay, and this will be our equation 4 here. And then if I add equation 3 and 4 together, well, they're set up nicely here, so I don't need to do any multiplying. Equation 3, 2x minus y equals -1. Equation 4, negative 2x plus y equals 1. And when I add these two equations together, I get 0 equals 0. Well, that's a nice answer, I guess. It does tell me I have a solution. It actually doesn't give me too much more information about the solution, but what I can conclude is that there are an infinite, if I can write, infinite number of solutions. So infinite solutions here. That doesn't mean we can plug in any old ordered triple and have it work as a solution, but there are an infinite number of solutions. What does this mean classification-wise? Well, our system is consistent because there's at least one solution. Those solutions that we would have here are dependent on each other. So we say the system here is consistent dependent. And graphically, that tells me that the three planes might intersect in a line as we have going on right here. All three planes could intersect in a single line. And along that line would be all of our solutions, which would be an infinite number of solutions would exist along that line. Try on your own number 1. Solve the system if possible and classify the system as consistent independent, consistent dependent, or inconsistent. We have the equations x plus y plus 2z equals 9, 2x plus 4y minus 3z equals 1, and 3x plus 6y minus 5z equals 0.